This is a newly discovered family of materials where electrons move in very strange ways. They can move left and right along the x-axis, back and forth along y, up and down along z, but they also seem to be able to move along a fourth fictitious dimension called zeta. Now, you and I can't move in four spatial dimensions because we're restricted to 3D, and technically these electrons are too. But they act like they can move along a fourth synthetic dimension. In fact, I'll show you that their motion is most intuitively visualized as an elliptic orbit that propagates in four spatial dimensions. The key difference between you and I and these electrons is that these electrons live in a Moiré superlattice, which is atomically incommensurate. It lacks translation symmetry. For the past half century or so, crystallographers who study the atomic structure of materials have known that incommensurate lattices like these are not actually incommensurate, but instead they can be modeled as projections of four, five, or six-dimensional lattices that we call superspace crystals. Even though superspace crystals live in higher dimensional superspace, they're a lot like regular 3D crystals because they're perfectly periodic and highly symmetric. Very importantly, though, if I take a very thin slice of the right superspace crystal, it can produce any incommensurate lattice that I find in nature. This entire mathematical framework is really elegant and beautiful, and it's been extremely successful in helping us understand how incommensurate materials derive their long-range order, how they crystallize in nature, and how they diffract under X-ray irradiation. Today, my teammates and I are really excited to share with you a new paper on arXiv, where we show for the first time that a new family of materials can host the electronic and magnetic properties of higher dimensional superspace. In this talk, I'll tell you about how we can grow tunable versions of Moiré superlattices in bulk crystals. And then I'll show you how we can use these new types of lattices in order to demonstrate a generalizable approach for simulating the properties of four-dimensional quantum materials. Thanks for joining me. My name is Kevin Knuckles. I'm a Pappalardo postdoctoral fellow in physics at MIT with Joe Jakelski. And today I'm really excited to share with you a story of fermiology, which is the study of how electrons move in metals and what Fermi surfaces and band structures guide that motion. As many of you know, fermiology has this long and storied history dating back to roughly the 1950s, and it's been a really great tool for physicists to be able to visualize the shapes and sizes of Fermi surfaces in metals. On one hand, this gives us an understanding of the fundamental properties of metals more basically. But in addition to that, fermiology oftentimes gives us a great starting point for understanding a much wider variety of quantum phenomena and materials related to correlations, topology, and superconductivity. And so today I'm excited to tell you about fermiology as studied in a new class of materials that we designed to emulate many of the salient properties of Moiré materials. More broadly, over the past decade or so, Moiré materials have really revolutionized how we control and design quantum phases of matter of nearly every type. Through either the rotational misalignment of 2D atomic crystals or the lattice mismatch of these crystals, we can produce these incommensurate lattices that have these long wavelength interference patterns, which we call Moiré superlattices. For much of this research, we've been excited as to how Moiré materials can generically access flat electronic bands. But this budding field, is going in many different directions. There are many angles for trying to engineer material properties that go beyond the flat band paradigm. So a couple of my favorite examples from this community are the fact that our community has learned that you can twist nonpolar materials like hexagonal boron nitride to produce Moiré ferroelectrics with spatially modulating polarization vectors. Our community has also seen that you can twist isotropic magnets like chromium triiodide in order to produce very intricate spin textures, non-collinear magnetism. Finally, our community has seen that you can twist high-temperature superconductors, which preserve time reversal symmetry, in order to produce interfacial superconducting states that appear to break time reversal symmetry. So all of these are really excellent examples of how we can use Moiré band material engineering to design the material properties of 2D materials. And so if I had to very generally, all under one umbrella, categorize what I mean by Moiré materials today, I would say that Moiré materials embody four key properties. The first is that they're atomically incommensurate. They have no local lattice order, and therefore they don't have a strictly well-defined Brillouin zone. Because of this incommensurability, they also derive a long wavelength modulation, which we call the Moiré superlattice, that is on the nanometer scale, set by the interfacial relaxation of these 2D atomic crystals against one another. Really importantly, Moiré materials have Moiré superlattices that are tunable without having to affect any of the chemical composition of their layers, oftentimes tuned by the twist angle that you set between the two crystals. And finally, with this tunable structure comes tunable low-energy physics that is often not found in the constituent layers. So a lot of experiments have been really focused on how this affects the Fermi surface or the band structure of Moiré materials, how this can affect interlayer coupling, or how this can give rise to a wide variety of quantum phases of matter. So in the past decade, all of this research has been really pioneered by a really useful tool that we call the van der Waals transfer station. Because the van der Waals transfer station allows us to assemble exfoliated van der Waals flakes of many types at low temperatures. So this is a great tool for doing 2D research because it's highly versatile. Effectively, any 2D material that I can exfoliate down to thin flakes, I can produce a Moiré material out of it by twisting and stacking these. Indeed, it's also highly generalizable. If I want Moiré materials with multiple incommensurate interfaces, I just pick up more materials. I can assemble all of these at low temperatures and form devices out of them. So this has been the workhorse of 2D research for the past maybe 20 years or so. But today, I want to introduce you to a conceptually new approach to designing high-quality Moiré materials through the high-temperature chemical synthesis of bulk van der Waals compounds. So the idea is that we're actually going to try to grow with solid-state chemistry bulk crystals that have all of the salient features of Moiré materials and probe their physical properties. And the key advantages of this approach are the fact that because we're growing these Moiré materials in thermodynamic equilibrium, they'll be highly homogeneous. The Moiré superlattices in these compounds will be nearly perfect throughout the entire volume of these millimeter-sized crystals. And because we're growing these crystals using solid-state chemistry, the Moiré superlattices are highly reproducible and potentially scalable for next-generation electronics that leverage Moiré materials. So how would we go about doing this? How would we try to design bulk crystals that have Moiré superlattices? There's a couple ways to design incommensurability in bulk crystals, and one of those approaches was one that we leveraged from the literature. So in order to introduce that idea, let's consider a simple thought experiment. So consider I have van der Waals compounds, two of them, and they come from different crystal systems. So on this left side is a hexagonal crystal with a hexagonal unit cell, and over here, the blue crystal is a monoclinic crystal with a monoclinic unit cell. I'll remind you that in this layer configuration, hexagonal and monoclinic crystals are actually very similar, but monoclinic crystals are a little less symmetric. In fact, monoclinic, one free angle. So this unit cell has an angle in its unit cell that is not something round like 120 degrees, but it's something random, like 105 degrees or 112 degrees, something not round. So these crystals, experimentally, would be identified by their symmetries in diffraction. So the idea is that I would place one of these single crystals in X-ray and irradiate X-rays into that crystal, collect the Bragg scattering peaks, and analyze the symmetries of the X-ray pattern in order to understand the symmetries of the unit cell. So we can identify hexagonal crystals by their hexagonally symmetric Bragg scattering peaks. So these are 6-fold symmetric. And we'll identify monoclinic crystals because their diffraction pattern is 2-fold symmetric, where we can identify a monoclinic angle in that diffraction. So the thought experiment goes like the following. Let's say that I wanted to stabilize a new foliated superlattice structure, effectively shuffling the deck of cards into a combined superlattice that is the natural intergrowth of these two monolayers. And what are the ways that I can do this physically? I think if you stare at these unit cells carefully, you'll recognize that I can't do so by satisfying all of the crystal symmetries of both systems simultaneously. That these are competing in interest, particularly this free angle is incompatible with this 120-degree angle. And so I can't do this atomically commensurately. But in some situations, there are accommodative reaction products that can satisfy a partial subset of the allowed symmetry constraints. So here's one that the misfit layered compounds in the literature took. So if you align the rightmost Bragg planes of this hexagonal lattice with the rightmost Bragg planes of this monoclinic lattice so that they're atomically commensurate in one of the two in-plane lattice directions, I'll effectively satisfy half of the symmetry constraints of these crystals, but in doing so, the system will necessarily be aperiodic in the orthogonal direction. And so essentially what we're doing is we're leveraging interlayer lattice frustration between these two different competing crystal systems in order to stabilize and enforce atomic scale incommensurability in thermodynamic equilibrium. I'll actually be able to grow this. This is a really great tool because there's basically no reason that I should be able to reach into a high temperature furnace and pull out twisted bilayer graphene. It has no symmetries. There's no reason why this would be energetically stable. And yet, here is an alternate route to trying to stabilize atomic scale incommensurability in something that actually could be thermodynamically stable. What the misfits didn't give us was the fact that these misfit compounds are typically hexagonal transition metal dicolchinide layers with rock salt, cubic rock salt layers. Cubic rock salt layers like lanthanum sulfide or lead selenide. These cubic layers are very different symmetries than the hexagonal layer, and they have very different lattice constants. And so they don't couple in interesting ways that morph the structural modulations of the hexagonal lattice. But here, monoclinic crystals and hexagonal crystals are much closer in symmetry, and we'll choose ternary phase diagrams where we can find these lattice constants that are very similar. And so because of similar symmetries, similar lattice constants, we'll find that what these superlattices will want to do is relax into new Moiré superlattices in bulk crystals. So this target reaction product we would call an aperiodic composite crystal. It's a crystal because it's a rock that I pull out of a high temperature furnace. It's aperiodic because it doesn't have translation symmetry. And we would call it a composite crystal because it's made up of these two different sublattices. It's effectively half hexagonal, half monoclinic. So this crystal, just like these simpler crystals, can also be identified by its symmetries and diffraction. So we should expect to see the hexagonal Bragg peaks superimposed upon the monoclinic Bragg peaks. There will also be two key signatures that we should look out for to identify Moiré superlattice versions of this. So the first is because these systems have very similar lattice constants, we'll be able to see a small wave vector in momentum space Q that separates the two Bragg peaks. So essentially from a Q vector that goes from the hexagonal lattice to the monoclinic lattice, because they're not quite commensurate with one another. They're not quite on top of each other. There's a small lattice mismatch. Furthermore, this small lattice mismatch will seed a long wavelength interference pattern, which we call the Moiré superlattice, which we'll be able to see directly in diffraction. And so this gives us really clear observations of what we should expect for a Moiré modulated aperiodic composite crystal, and we'll in turn try to stabilize this type of crystal, but also try to tune its structure using solid state chemistry. So without further ado, let's jump into some of these crystals. Here are some aperiodic composite crystals that I discovered in the strontium tantalum sulfur ternary phase diagram. You can see they come in a wide variety of macroscopic crystal facets, depending on how you grow them, but they're all plate-like, and they're all exfoliatable van der Waals crystals. So here's me exfoliating using Scotch tape. You can see the crystals, they copy nicely onto regular Scotch tape, and we can deposit them onto silicon dioxide. These crystals over here with AFM we saw were about 10 nanometers thick. I think you could probably exfoliate them thinner. I didn't really try. I hope that the community tries further, but they clearly exfoliate like graphite or TMDs. So with these diffraction signatures in mind, we'll do a single crystal X-ray diffraction to understand the symmetries of these lattices. And so when we perform these measurements, we see a very dense, complicated spectrum of diffraction peaks that are hard to make sense of at first, but we recognize that we can use a lot of symmetries of this diffraction pattern in order to pull out the different sublattices. So the first is that these red circled peaks in the diffraction pattern, these are six-fold symmetric, and so they have to be associated with a hexagonal sublattice. Whereas these blue peaks right here, these are twofold symmetric, and I can identify a monoclinic angle in the diffraction pattern. So they have to be associated with monoclinic layers. There are actually a lot of other peaks in this diffraction pattern that are unassociated with the individual layers, and it's hard to know what these come from without a higher resolution probe. So we first start with single crystal X-ray diffraction because it allows us to verify out to many, many Bragg zones that the monoclinic and hexagonal layers are atomically incommensurate. They don't ever line up out to many, many Bragg zones. But we then use a higher resolution X-ray diffraction tool called wide-angle X-ray diffraction, which is higher resolution, but it's more myopic. So I can't see quite as far in momentum space. So using this high resolution X-ray diffraction technique, we find that indeed the hexagonal and monoclinic layers are separated by a very small wave vector q, where that same q vector is emulated around the center for a long wavelength incommensurate modulation, as well as it explains all of these satellite peaks. And so this is really great that the lattice mismatch, the incommensurate modulation, and all of these satellite peaks are explained by exactly the same wave vector q. They all have this one q vector that appears everywhere. It's nice to see it in diffraction, but I also like seeing it in real space. And so collaborating very closely with David Bell's group at Harvard, we did cross-sectional TEM images of these types of compounds. So this is a different batch. It's not the same batch as the previous slide, but it has the same lattice motif. And we're now cutting through all the layers and imaging the cross-sectional image of the layers. And you can see indeed the structure of this foliated superlattice. So it's the natural intergrowth of different monolayers in this bulk crystal. And we can identify these bright regions here. These are the tantalum disulfide hexagonal layers, and these are monolayer metals. Whereas we can also identify crystalline monolayers of strontium-6, tantalum-sulfur-8, which are monoclinic, and they are effectively, we don't expect them to be electronically active, but they do couple in interesting ways, symmetry-related ways to the tantalum disulfide to produce the Moiré superlattice. So there's a couple things I want to point out about these types of images in TEM. The first is if you take a line cut along the spacer layer and you project the intensity of the TEM image, and you take a line cut of the hexagonal layer nearby, and you try to project them against one another, you'll see that they are atomically incommensurate, that this interface is incommensurate in real space, indeed confirming what we saw in X-ray diffraction. The second thing is that because we're cutting through the cross-section of this crystal, we can see this warping of the layers, which is exactly warping with the Moiré wavelength. So this is seeing that the crystal layers are trying to interfacially relax against one another because of the incommensurability, exactly as we see in 2D Moiré materials. So this is a further confirmation that the Moiré superlattice is a dominant scattering vector. It's a dominant energy scale in this crystal formation. So putting this together, these real space images with diffraction images and some chemical probes, we assemble a high symmetry model structure of this aperiodic composite crystal. So this crystal is made up of two different layers, strontium-6, tantalum-sulfur-8, and tantalum disulfide in this layer by layer intergrowth. And because of diffraction, we can now assemble a structure of the top-down interlayer coupling of the Moiré superlattice. So this is an image, a reproduction of what you would see when you look down at how these two layers couple to one another. And the parallelogram here is the spacer layer's unit cell. So here is where we can see half incommensurate, half commensurate lattice structure. So you can see that this unit cell, this top edge, is commensurate with this spacer layer, and it's commensurate with this tantalum disulfide layer. And so this is the commensurate direction, the vertical b-axis. Whereas the orthogonal direction, you can see that the parallelogram is commensurate in the spacer layer, but it's incommensurate with the tantalum disulfide layer. So this is the atomically enforced incommensurate direction of the lattice. And so putting this all together, this aperiodic composite crystal manifests our design principle because they have similar symmetry, similar lattice constants, and so they produce a Moiré modulation in a bulk crystal. So with this crystal in hand, I think it's good to think that we could try to tune the superlattice, Moiré superlattice in this crystal using the tools of solid-state chemistry. And the idea here is that if this system is truly aperiodic, then the free energy of this crystal should be very flat. And so we should be able to stabilize a whole bunch of different incommensurate lattices because there's no one structure that is optimally favored in this phase space. Before I get into some of the chemistry, though, I think we need to revise this name. So I introduced this strontium-6, tantalum-sulfur-8, 1 plus delta, where delta is not rational, and tantalum disulfide 8. This is a really egregious version of trying to name a chemical compound because it's very clunky, it's hard to say, and particularly it doesn't tell me anything about the Moiré superlattice. So we propose an abbreviation that captures more of the dynamics of the Moiré superlattice. So it's strontium, tantalum, sulfur, so we'll call it STS. And then we'll use two indices, one that captures the commensurate aspects of the Bruins of the interlayer coupling, and one that captures the incommensurate aspects of the in-plane lattice. So this commensurate index n is an integer, and effectively it just tells me how many of the Bragg planes are shared between these two lattices. So you can see very specifically in this compound, the top and bottom of this unit cell in the spacer takes 1, 2, 3, 4, 5 unit cells in the tantalum disulfide, so n equals 5. And then the incommensurate index could be the wavelength of the Moiré superlattice or the length of the Q vector, but we decided to take the angle of the Q vector with respect to high symmetry directions, namely because it's really easy to read out through X-ray diffraction, but it's also much easier to say. And so with n equals 5, phi equals 72, we would call this Moiré compound STS 572. If you didn't understand that naming scheme, it doesn't matter for the rest of the talk. Just recall that STS means strontium, tantalum, sulfur. And if these two indices are different between two different compounds, they have different Moiré superlattices, although they're chemically identical. So with a lot of tools in solid state chemistry, we can vary the growth profile, the temperature profiles, the starting precursor stoichiometries, and the types of catalysts to grow these crystals. We found that there are a wide variety of Moiré superlattices that all have the same stoichiometry from chemical probes like wavelength dispersive spectroscopy. They seem to stabilize a bunch of different diffraction patterns, which tells us that the Moiré superlattice is distinctly tunable in this phase diagram from about 3 nanometers to about 4.5 nanometers, various different directions. So altogether, these compounds seem to stabilize chemically identical TMD, tantalum disulfide, and spacer, strontium-6 tantalum sulfur layers that intergrow in a wide tunable spectrum of in-plane Moiré superlattices. At first, when we kept discovering these in crystal synthesis, it was very perplexing because I'm not using a transfer station to produce any of these Moiré superlattices. So what gives? How could I be stabilizing so many different compounds, but they're all chemically identical? So the key comes from X-ray diffraction, and it tells us that this tantalum disulfide layer in X-ray diffraction is very rigid. It basically occurs with the same lattice parameters every time. But this monoclinic layer can strain and shear in minute ways because the Moiré superlattice is an interference effect, that minute changes of the lattice constants of this guy produce very big distinctive signatures on the Moiré superlattice, very different Moiré superlattices that are again directly read out through X-ray diffraction. To really visualize that, I think that we have a simplified diagram where we can display this hexagonal lattice of tantalum disulfide as a perfect hexagon, and we can we can depict this monoclinic lattice first as a perfect hexagon, then we will strain and shear it into its monoclinic symmetries, so you can see it's a bit skewed. And we'll try to layer these on top of one another using all of the diffraction patterns that we quantitatively extracted through our measurements. So in doing so, we can understand the coupling between these layers, and you'll see that one of our compounds, STS-390, is our structurally simplest Moiré metal. So you can see it's perfectly atomically commensurate in the vertical B-axis, but in the A-axis, it's very simple. It just has a long wavelength, 3.2 nanometer modulation, the Moiré superlattice. So this is a very simple structure, and it will be the focus of many of our measurements later in this talk. Whereas other compounds like STS-572 and 881, these are a bit more complicated because in addition to their Moiré superlattice, they have additional commensurate aliasing in the commensurate direction. So their commensurability is achieved over many unit cells. So again, I'll stress that these are all strictly one-dimensional Moiré superlattices, but they can mimic or approximate quasi-2D Moiré superlattices because this AA site is related to this AA site by a long translation vector, a very long wavelength, but a commensurate translation vector. Whether or not the electrons really know this semantic or whether they feel like they're in a Moiré superlattice, kind of don't know at this point, but I'm hoping the next year we'll have more experiments to be able to tease out this subtlety. So a couple of things that pop out to me when we're analyzing these natural Moiré superlattices grown in thermodynamic equilibrium, especially when we compare to more typical 2D Moiré superlattices. So to illustrate that, here is one of those schematic diagrams of STS-572, one of the Moiré superlattices that we discovered. And you can see that it has a 1D Moiré superlattice that points at this weird direction of 72 degrees with respect to its high symmetry crystal axes. So this is depicted as a simulation of the X-ray diffraction pattern. But really perplexingly, if you look at these crystals under an optical microscope, you can actually find obvious crystal step facets and even macroscopic crystal facets that all align to the 72-degree angle. So this is really beautiful. This is a macroscopic signature of the crystal's Moiré superlattice in optical microscopy, likely a vestige of the crystal formation process. This is highly unintuitive to me as someone who made twisted bilayer graphene devices, where if you warm them up a little bit, oftentimes they just relax and they reduce their Moiré superlattice. But this suggests that in bulk Moiré materials, the Moiré superlattice can not only offer a competitive energy scale for crystal formation, but in some situations, it's a candidate for the dominant energy scale for stabilizing this compound. Yeah, really beautifully unintuitive. I don't understand why this is the case, but for STS-5 and STS-13, this is basically always the case. Every crystal looks like this. In addition, because we're growing superlattices in thermodynamic equilibrium, when you do diffraction on any crystal within a batch with the same growth profile, with the same catalyst, with the same precursors, you find identical diffraction patterns. Particularly, these Moiré superlattices are highly reproducible. And so if you're interested in using Moiré materials for next generation electronics, I implore you to use chemical pathways that emulate some of the chemistry that we've discovered and discussed in our paper. So with such tunable structures, we want to understand how this tunable structure imparts itself on tunable material properties, and what better way to test this than to analyze the Fermi surfaces of these bulk Moiré metals. So the workhorse probe for these Fermi surface measurements will be torque magnetometry, which in my opinion is one of the most sensitive probes of quantum oscillations in bulk materials. So a brief refresher, torque magnetometry works where I have a single crystal that I affix to the end of a silicon nitride cantilever, and I place this thing into a magnetic field. And if this crystal is isotropic, then in linear response to the magnetic field, the magnetization of this crystal will point directly into the magnetic field's direction. And so this crystal will feel nothing. But if this crystal is anisotropic in any way, like it has an out-of-plane and in-plane magnetic susceptibility that are different, then this crystal's magnetization will not point in the magnetic field direction. And so this crystal will feel a torque, tau, which looks like the magnetization crossed into the magnetic field, which will try to deflect the crystal into the magnetic field, into a lower energy configuration. The Hospen-Alfvén oscillations are oscillations of the magnetization, so we can read these out through torque magnetometry because we have really sensitive circuits for measuring the deflections of these cantilevers, and we have very stable setups that are stable up to extremely high magnetic fields, as we were able to use at MagLab at Tallahassee, Florida. So we did a bunch of these experiments, and there were a couple that stood out to me as particularly incisive probes of the Fermiology. So one of these experiments was that we had different crystals grown from different chemical synthesis recipes that had Moiré superlattices that are super similar. So they basically have the same commensurate Brillouin zone folding, the same very, very nearly the same Moiré superlattice wavelength, but the Moiré superlattice points along different directions. So this compound SDS-881 was grown at much lower temperatures and grown relatively quickly, and it stabilizes a Moiré superlattice that points in a low symmetry non-crystallographic direction, whereas SDS-890 was grown at much, much higher temperatures and cooled super slowly in order to sweep the Moiré superlattice into this high symmetry direction. So we can perform torque magnetometry between these two types of crystal batches and compare them. And so we plot here the background subtracted torque magnetization, which just gives me the oscillatory portion of the torque magnetometry signal as a function of magnetic field up to 32 Tesla as given to us at MagLab. So you can look at these quantum oscillations, and you can see that they look very similar, but they're clearly different, even just at the oscillation point of view. You can see that these signals are different. Onsager would suggest that we try to make this statement a bit more quantitative, because Onsager tells us that the frequency of quantum oscillations is directly proportional to the extremal Fermi surface area in K-space of that pocket. So effectively, the frequencies are going to give us the sizes of Fermi pockets. And so we Fourier transform signals like this, and we see that these Moiré metals have a dense cascade of low-frequency pockets, very small Fermi pockets in momentum space. Through a careful analysis of these two, you can actually find that these Fourier transforms are clearly different, but they're quite comparable. And so we can see by comparing different peaks that actually, in many situations, most notably, if you rotate the Moiré superlattice from a low symmetry direction to a high symmetry direction, many neighboring peaks appear to merge very cleanly into sharp peaks, whereas this double peak right here appeared to split very nicely in the high symmetry Moiré superlattice. So this suggests, through Onsager's relation, that the Moiré superlattice in these compounds is reshaping and resizing the Fermi pockets of bulk crystals as programmed through their chemical synthesis conditions. So bringing this all back to the beginning of the talk, we had these qualities of Moiré materials that we should revisit. So these bulk Moiré metals that we've discovered are atomically incommensurate, that have long wavelength Moiré modulations. Indeed, we can tune the Moiré superlattice without trying to change any of the chemistry of the component layers. And that tunable Moiré superlattice directly imparts itself on the shape and size of the Fermi surfaces, Fermi pockets in these Fermi surfaces. Indeed, confirming that our bulk Moiré metals have all the same characteristics as more typical 2D Moiré materials. So with the time I have left, I want to tell you about a deep dive into the fermiology of our structurally simplest and our highest mobility Moiré metal that we discovered in this entire phase space. So I'll remind you of that structure. We call this compound STS390, and it's our structurally simplest bulk Moiré metal because effectively the only interlayer coupling effect that we see is this long wavelength Moiré modulation of about 3.2 nanometers. And so this will give us a really nice testing bed for understanding the distinct influence of a Moiré superlattice in just an isotropic clean metal. So we performed a couple of these experiments. Here I'm showing two representative crystals, taken experiments that were done on different magnetic field days at MagLab, and we're again performing the measurements of the background subtracted torque magnetization all the way up to high fields. And you can see that these magnetization measurements are highly reproducible throughout these batches. So the quantum oscillations are beautiful, and they basically align up to like the phase of the oscillation in these crystals, highly reproducible. Although quantum oscillations onset at very low fields, like 0.5 Tesla, they don't seem to trumpet out in amplitude at higher fields. If you did quantum oscillation studies on something more typical like graphene, then you would find that a small quantum oscillation at low fields would become a very large quantum oscillation at higher fields. And that's not what we're seeing here, because there are actually many frequencies that are being represented in this Fourier transform. And so these many separate frequencies are destructively and constructively interfering to create this rather constant amplitude magnetic amplitude signal that we see at all magnetic fields. So Onsager would again implore us to make this statement more quantitative and to Fourier transform these. And we find nearly identical Fourier transforms that are very complicated in this crystal. So like the other bulk Moiré metals, we have this dense cascade of low frequency pockets, but now this cascade persists all the way up to much higher frequencies, much bigger pockets. In total, in comparing these two measurements that I'm showing you in the main text, we find that approximately 45 different quantum oscillation frequencies or cross-sectional areas are shared between these measurements, which to our knowledge is the most that's ever been seen in a metal. So this is a really complicated signature to try to make sense of, especially when we have very few structural features and no signatures of charge density waves in this compound. But there are a couple of features that we found of the data that pointed us along the right direction to understand that maybe they're all being produced by a common origin. So two important plots. The first is that we took temperature dependence of these quantum oscillations, and we can quantitatively extract from that the effective mass of the Fermi pockets. And so here I'm plotting the effective mass of those pockets as a function of their frequency, so effectively the scaling of the size of the Fermi pocket. And from this plot, we see nothing of note. They're effectively kind of normal Fermi pockets. They're slowly drifting from 0.5 bare effective masses up to 1.5 bare effective masses. There's not much of note in this plot. And really importantly is that there are many non-Onsager mechanisms in the literature that generate new frequencies that are unassociated with a new extremal Fermi surface pocket. So examples of this are magnetic breakdown. I have two neighboring pockets, and at high fields, the electron can tunnel to encircle both of those pockets and generate a new frequency. Or quasi-particle lifetime oscillations, which are virtual processes between two pockets, or Weiss oscillations, which are effectively geometric resonance signatures. There are many of these that are detailed in our supplement, and nearly all of them have very distinctive signatures in effective mass. So if I were to generate 45 different new pockets from magnetic breakdown, I would expect the effective mass of those pockets to skyrocket up to 45 bare effective masses, or plummet down to 1/45th of an effective mass. And we're not seeing that. So effectively, what we're seeing are normal Fermi pockets in these measurements, although it's a really chaotic, complex band structure. This is a bunch of null hypotheses, but the plot that really points us in the right direction is the fact that we can just plot the frequency or the proximate area of that Fermi surface just as a function of peak index. So just to enumerate 1, 2, 3, 4, 5, 6, 7 as we see in the Fourier transform. And we find that throughout nearly the entire frequency range, we find them roughly linearly spaced. All 45 peaks fall on this linear spaced line. So the idea here is that the Fermi surface in this simple Moiré metal is just chaos. It has 45 different pockets. But if you slow down and look at the Fermi pocket sizes for a sec, you'll find that one Fermi pocket is incrementally bigger than another one, is incrementally bigger than another one, and they're all separated by this anomalous area that is not represented in the Fourier transform. And so it's not something, like an artifact from the measurement. It's actually, these pockets are all deriving from some extra area that is not part of the Fermi surface. So this is a really distinctive signature, and it really points us in the right direction. And in order to understand this signature and the complex experimental signatures of this Moiré metal, I think we'll need to address a much broader idea of how is it possible even for an incommensurate metal that doesn't have a well-defined Brillouin zone, how could this quantum oscillate? It doesn't have translation symmetry, it doesn't have well-defined crystal momentum, and so I don't even really understand what a coherent cyclotron orbit should look like. So this is a complicated problem, but luckily, it reminds me of a related problem that was solved in the 70s from the study of incommensurate crystallography. So this is a bit of a history aside, but I think it's really important to remember that in the 1960s, the world believed that all matter was either crystalline or amorphous. But experiments discovered new types of crystals, particularly aperiodic composite crystals and quasicrystals, which evaded those locally symmetric unit cell driven compounds that were dominated in previous studies. So these crystals, aperiodic composites, these are the ones that we've been studying in this talk already. Two different sublattices that are incommensurate with one another, and quasicrystals, which also have no local unit cell, but they have no average local coordination. It changes as a function of position. So when people started discovering these, they had many examples, and they became very perplexed because although if you look very carefully, up close at the lattices of these incommensurate lattices, they look disordered. But if you do diffraction on these crystals, you find diffraction is beautiful. Diffraction has a dense array of sharp diffraction peaks, where the sharpness of these diffraction peaks is often comparable to what you'd expect of a purely periodic lattice. This makes no sense if you take it, at face level. If you look locally, lattice doesn't look like it has all of the ingredients to constructively and destructively interfere to produce a sharp diffraction peak. And so this had people puzzled for quite some time, but theoretical physicists have solved this now with some really beautiful mathematical framework. So what theoretical physicists recognized was that incommensurate lattices are not actually incommensurate, but instead they can be understood as projections of 4, 5, or 6-dimensional, higher dimensional lattices that we call superspace crystals. I'm not going to have time to go through all of this formalism, but I do want to motivate it with a kind of interesting illustration. So here is a picture of an aperiodic composite crystal. It has two different sublattices that are incommensurate with one another, the orange and blue. I can't draw in 4D, but I can draw in 2D. And so let's isolate this 1D line cut, which is also incommensurate. And I argue that this one-dimensional incommensurate crystal is equal to this 1 plus one-dimensional superspace crystal. To understand this construction, we have this physical dimension, and I've elevated the structure into one higher superspace dimension. And then if we project from the superspace dimension back into the physical dimension, we recover the incommensurate lattice. So this seems like a party trick, but actually I assure you that it works for all incommensurate lattices seen in nature. And it's the thing that endows incommensurate lattices with long-range order, with sharp diffraction peaks. And so looking at this problem, we think that this is very related to our current problem in our paper. So the dense arrays of sharp diffraction peaks seen in incommensurate lattices, and this dense array of sharp de Haaspann-Alphen frequencies that we observe in an incommensurate Moiré metal. We both believe that both of these ideas can be similarly rectified by elevating incommensurate structures into emergent synthetic superspace dimensions. In the 70s, people recognized that there are some constructions for producing superspace crystals based on lattice mismatches in real space. And we'll show that we can actually understand these quantum oscillations from a kind of momentum space analog. We'll project it from higher dimensional Fermi surfaces, and particularly a 3 plus 1-dimensional Fermi surface, will project down into our physical space. And this is generated instead of by lattice mismatches, but by momentum mismatches due to the Moiré superlattice. So we kind of had a feeling that this might be true, that there might be some connection, but it was really gratifying to see that a lot of this popped out of just standard Lifshitz-Kostovic theory for understanding Moiré metals. So in collaboration with Nisarga Paul and Filippo Gaggioli and Liang Fu at MIT, we were able to understand a lot of this through Lifshitz-Kostovic theory, which is a generic framework for understanding quantum oscillations as it relates the oscillatory part of many thermodynamic quantities to extremal Fermi surface orbits. So this is a general starting point for understanding quantum oscillations in conventional metals. And at its core, this theory has these two major components. First is this Onsager area relation, which we've been working with earlier in this talk, which tells us that the frequency of quantum oscillations is directly proportional to the extremal area in K space of a Fermi orbit. So this is taught to us in solid state physics, but there's a second component that I don't remember learning in solid state physics, but is equally important, and it's the Onsager quantization rule, which tells us that as this electron performs its cyclotron orbit in k-space or in real space, the wave function has to be 2 pi periodic because the wave function is single valued. So essentially, as I move around in my cyclotron orbit in real space, the phase of the wave function oscillates, but it has to come back to itself. So these types of rules are known in conventional metals, and our theory colleagues at MIT understood that you could actually make calculations for an incommensurate 1D modulation in our Moiré metals. So what they found rigorously through Lifshitz-Kossovich theory is that there are a sequence of coherently scattered orbits that scatter by the Moiré wave vector Q, 2Q, 3Q, integer multiples of Q, and this generates a non-Onsager set of frequencies that look like the frequency of the pocket plus this anomalous frequency plus 2 frequencies, frequency plus 3 frequencies with phase discontinuities. So in order to see that, the Onsager area relation is now affected with this new term that makes sure that this is no longer an Onsager relation. So the frequency is no longer proportional to the area, but it produces a linear set of frequencies where this extra frequency component is proportional to Q. So for Q to be super, super small, the Moiré wavelength is very, very long, we should recover the crystalline Onsager relation. And indeed, this factor goes to 0, and so we recover Onsager's relation. But when Q is finite, then each frequency in the Fourier transform of the unmodulated metal will split into a sequence of frequencies set by something that's set by the Moiré wavelength. Indeed, Onsager's quantization rule also gets affected by phase discontinuities, such that when we complete this orbit, we're no longer 2 pi periodic, but we're 2 pi periodic with an extra phase discontinuity. And so the idea is that in real space, the electron is moving in its cyclotron orbit, and its phase comes to this so-called hotspot in momentum space, where the direction of propagation of the electron is along the Moiré wavelength. And so effectively, this electron can scatter and pick up some phase discontinuities by integer multiple scatterings of the Moiré superlattice, and then it phase propagates again. And then when it comes back around, it staircases back down the other way. And so it's 2 pi periodic with these phase discontinuities, although these look really strange. So all of this framework is really nice because it gives us an understanding of what's going on in our system, that the Moiré superlattice is generating a coherent set of different cyclotron orbits that have these kind of scattered wave vectors. But this is a non-Onsager mechanism. Looking at this theory, it's mathematically satisfying, but intuitively it's very hard to picture, particularly because it has this weird phase discontinuity that I don't see familiar in quantum mechanics. But we were able to see that actually this is much more naturally understood when we elevate the system into 4 dimensions, into 4-dimensional superspace. And so bringing back that Onsager area relation and quantization rule, I actually will show you that this anomalous frequency, anomalous phase shift, they're not only proportional to Q, but they're proportional to this Q vector times the Fermi wave vector that is perpendicular to the Q. So if you look at this quantity very carefully, you'll recognize that actually this has the units of area in momentum space. Momentum, so it's a momentum squared. And so what this entices us to do is to take this form and to fold it back into the area in each of these Onsager relations in order to recover an Onsager area and quantization rule. And so effectively what we found in this mathematics is that there's an equivalent Onsager area relation and quantization rule that looks like a 4-dimensional cyclotron orbit in a 4-dimensional metal for some anomalous area that we need to motivate at this point. So there's some new total area that's producing this, although frequency is now proportional to area, and area produces 2 pi periodic cyclotron orbit. So graphically, we can take a lot of the construction from incommensurate lattices and try to figure out what that might look like in momentum space. And so if you were to elevate the Fermi surface, the quasi-2D or purely 3D Fermi surface, into one higher superspace dimension based on not the lattice mismatch, but the momentum mismatch of the crystal, and you'll find that this pocket is replicated along the staircase in synthetic dimension. And if I project down into the physical dimension, the cyclotron orbit now looks like I have an electron that propagates in this Fermi pocket. It hops an integer multiple steps of 2, 3, 7 number of times along the Moiré superlattice, and then it completes its orbit. And this whole area includes this anomalous 4-dimensional area, which is the momentum Q times the Fermi wave vector in the orthogonal direction. So effectively, this anomalous area is coming from the projection of this Fermi surface from 4D into 3D. Indeed, it's very satisfying to recognize that actually this phase discontinuity we saw in previous slides is very opaque, but it's exactly the amount of phase that you would expect to accumulate if you were to actually propagate in this anomalous, this synthetic four-dimensional space. And so putting this all together, we have effectively uncovered a mechanism that has one Fermi pocket that is oscillating in 2 dimensions in our 3D Moiré metal. But that Fermi pocket, because it is in a Moiré superlattice, it can generate a sequence of Fermi frequencies, which can be understood as non-Onsager frequencies in 3D, can also be understood as four-dimensional, simulating four-dimensional cyclotron orbits. So 4D Onsager frequencies of the same exact type as electrons coherently hop along this synthetic superspace dimension that's generated by the Moiré superlattice. It's generated by this momentum mismatch, and therefore this simulates orbits of 3 plus 1-dimensional Fermi surface. So 3 dimensions, x, y, and z, these are continuous dimensions. Then this extra dimension is a discrete dimension set by integer hoppings along the Moiré. So putting this all together, I think that this really suggests that these ideas, this real space and momentum space idea, are really closely connected in synthetic superspace dimensions. In fact, previous work has shown that this superspace crystal formalism is really important for understanding static properties like the charge density or the atomic lattices of incommensurate materials. But our paper is the first to show that actually dynamical processes like the Fermi surface of itinerant carriers can also be understood very naturally in superspace. So with that, I'd like to show you some outlook and particularly, look forward beyond where this paper will take us. And a lot of physics that discusses dimensionality, as we've discussed today, is related to this concept of holography in other fields of physics. This concept of holography is described as the relationship between a complete description of a higher dimensional system that emerges naturally from a lower dimensional encoded representation. So when we see this concept in other fields of physics, like holograms in classical optics, I can have this 2D optical film that projects into a 3-dimensional emergent image, although the emergent image is not real. You can look through this film and you can see something that looks 3D. We also have examples of quantum error correcting codes where physical qubits can be organized along a boundary and can project into emergent logical qubits that carry out computations, but they're not actually real. All the physical qubits are the ones that are real. And then this is very famously used in holographic correspondences in quantum gravity, where we have theories of quantum gravity that model quantum field theories that collect along the boundary and project into gravitational theories that sit in the bulk, suggesting that actually space-time, the whole universe, everything around us is all emergent from some boundary theory. So our work here stands to suggest that actually holography is a great way to understand these two different theories for quantum oscillations in Moiré metals. So we had this non-Onsager mechanism in 3 dimensions for producing all of the right observables. This is in 1-to-1 correspondence with a higher dimensional, 4-dimensional superspace theory for understanding these quantum oscillations much more naturally. And so we think that things like this should be emulated in many different directions in quantum materials research that allow incommensurate structures to simulate the ideas, the theories of higher dimensional physics. So a lot of ideas we can take from atomic, molecular, and optical physics, where they use lower dimensional optical lattices to produce higher dimensional topological phases. And I think aperiodic composites are a really great way to try to achieve topological phases in superspace dimensions. And there are also really beautiful theories out there for higher dimensional forms of unconventional superconductivity, which we think might be accessible through incommensurate lattices. And so we think more broadly that holography will describe this correspondence between incommensurate theories and higher dimensional periodic superspace theories, and that these synthetic superspace dimensions, as simulated by aperiodics that have the requisite symmetries for simulating higher dimensional space, this could have immense implications on correlation-driven topological and superconducting phases that have been proposed but now are possibly accessible in real materials in higher dimensions. So with that, I'll thank you for your time and thank the people responsible. Alan and I work very closely in Joe Jakelski's group. And then we received really indispensable theoretical help from Nisarga, Filippo, and Liang at MIT. Thank you.